Welcome to the Center for Filtration Research Virtual Lab Tour. This presentation will go through an example of 4 projects being worked on by the Center for Filtration Research, the first of these being the development of a bioaerosol sensor. An interesting project being worked on is the development of a bioaerosol sensor. This sensor aims to provide real-time detection and differentiation of bioaerosols in a portable package. As seen in the video here, the sensor is much smaller in scale than other alternatives. The main work being performed in the Particle Technology Lab is characterizing the performance of the sensor for various particle types and sizes. Shown here is an example of the experimental work being performed on the sensor. Specifically, detection of riboflavin particles over the size of 1 micron is being evaluated. As can be seen, the sensor is hooked up in parallel with an aerodynamic particle sizer, which allows for the counting and sizing of the tryptophan particles to be done. The particles, created using a flow-focusing aerosol generator, are filtered using a multiplet reduction impactor and split between the APS and the sensor. The sensor detection is currently run off a desktop program, allowing for the capture of detection videos. An example clip of the detection of 1 micron riboflavin particles is shown here. Here, a continuous flow is being sampled, with the particles being detected in real time. An image detection software is then able to count these particles, which can be correlated to the overall concentration of the aerosol. The previous example showed the sensor using the induced fluorescence signal of riboflavin to detect the presence of particles. While this is the main focus of the sensor development, specifically strengthening this signal and improving the countability of detected particles, the sensor is also able to use elastic scattering to detect the presence of all particles, not limited to bioaerosols. An example of this is shown for 2 micron NaCl. As one can see, the elastic scattering of the salt particles is even more clear than the induced fluorescence signal, allowing for easier counting and calculation of the corresponding particle concentration. The sensor still has large areas for improvement, with some of them being listed here. These include improving the strength and clarity of the induced fluorescence signal to allow for higher counting efficiency, building upon the current design to allow for lower concentration detection limits, improving the image detection software to better count all detected particles, and many more. Overall, the bioaerosol sensor represents an exciting project that will have many avenues of potential expansion and application, and is just one of the projects being worked on by the Particle Technology Lab. The second project will focus on a medium-scale wind tunnel. Pleated air filters are used in a variety of filtration applications, such as HVAC, automotive cabin air, pharmaceutical clean rooms, and many more. By pleating the filter media, filters offer higher filtration efficiencies with optimized pressure drop to reduce energy use during operation. This video shows a brief description of a new medium flow rate wind tunnel developed under the Center for Filtration Research sponsorship, designed to measure the integral efficiency of pleated filter panels and the filter pressure drop at a known flow rate. Components of the wind tunnel are an inline fan, an orifice plate flow meter with a pressure transducer, a temperature and relative humidity probe, a pressure transducer to measure filter panel flow resistance, the upstream and downstream sampling ports that connect to a condensation particle counter through a 3-way solenoid valve. The aerosol generator to inject particles upstream of the filter at a high concentration, and a HEPA inlet filter at the wind tunnel air intake. The pleated filter to be tested is installed in the middle section of the tunnel by means of a mounting plate. The filter panel must be perfectly sealed on its perimeter by using duct tape to prevent particle leakage through the panel edges. When the air is flowing through the filter, the pressure drop is measured using pressure taps directly upstream and downstream of the filter panel, which are connected to a differential pressure transducer. A condensation particle counter is used to measure the total particle concentration upstream and downstream of the filter panel. A LabVIEW interface program is used on a laptop computer to communicate with all the sensors and to automate the data collection. During the test, a solenoid valve is used to switch between the upstream and downstream sampling ports, connected to the particle counter. The automated program sequence collects the measured flow rate, pressure drop, temperature, humidity, and particle counts upstream and downstream of the filter. In this clip, you can see the CPC downstream concentration of about 100 particles per cubic centimeter switching to the upstream sampling port at about 45,000 particles per cubic centimeter. When the test sequence is completed, the screen shows the summary of the test results with the penetration, filter efficiency, flow rate, pressure drop, temperature, and relative humidity all displayed. The data is also stored in the laptop computer. In this way, many types of pleated filters can be characterized experimentally in a repeatable and consistent way. The third project will focus on digital filter modeling.
Whether for newly designed or existing filter materials, computer-based simulations provide a comprehensive understanding of the geometric and physical properties of filters. Another interesting work we are doing is digital filter material modeling and design. In addition to utilizing modern numerical simulation tools like ANSYS Fluent and COMSOL Multiphysics, our laboratory is equipped with Geodeck, a cutting-edge 3D porous material simulator. This is the interface of the Geodeck software. It includes dozens of modules covering the 3D image processing, design of the filter microstructure, material properties, characterization, filtration performance prediction, and optimization of complete filter element design. Here are some examples. With a numeric simulation, we can study the movement of particles flowing across individual or several fibers. By simulating particle behavior at this microscale level, we can better understand the underlying mechanisms governing filtration process. Also, we can simulate the loading process of airborne particles as they are captured and retained by the filter over successive time intervals. This dynamic analysis offers valuable insights into the filter's performance degradation and lifespan, enabling us to optimize its design. As the simulation capability extends to the microscopic level, allowing us to zoom in and track the trajectory of individual particles as they navigate through the fibrous network inside the filter. Moreover, it allows to reconstruct types of filters with X-ray CT image data and predict their filtration performance. At a larger scale, with the numeric simulation, we can optimize our filter element design and predict its service lifetime. In addition, we have the web-based filter modeling and design tool developed by our lab. It has a user-friendly interface and allows us to have a quick estimation of filter performance, including filter analysis, dust loading prediction, and pleating design with several input parameters, which is really popular with our CFA members from the filtration industries. Here are our main ongoing modeling projects. Just contact us if you are interested in these topics.
The fourth project will look at eco-friendly nanofiber research. We are focusing on nanofiber research as one of our sustainable and eco-friendly research topics at the CFR. Nanofiber research is said to be an important technology that can reduce pressure drop using the slip effect. In addition, the CFR is conducting research on eco-friendly nanofibers. This is a technology that generates nanofibers using eco-friendly polymer materials as well as eco-friendly solvents. An example of this is using eco-friendly nanofibers in an electrospinning machine. First, prepare a solution in which the polymer is dissolved in a solvent. Put it in a syringe and fix it to the syringe pump. Then install the syringe pump to the electrospinning machine. In addition, the flow rate supplied to the nozzle can now be set. The flow rate may need to be adjusted to generate nanofibers stably. The supply voltage setting to the needle is an important parameter to consider for nanofiber diameter and stable spinning. When high voltage is applied to the needle, a Taylor cone is formed with the edge of the needle due to the surface tension of the polymer solution and the electrofield between the needle and the collector. In order to make a large area filter media and increase uniformity by collecting nanofibers along the collector, the needle can be moved left and right. The CFR plans to conduct more research on sustainable electrospinning processes in the future. In addition, we also plan to conduct research considering mass production using eco-friendly nanofibers. These projects show just a snippet of what's being worked on in the Center for Filtration Research. If you have any interest or questions about any of these projects, please feel free to reach out. Thank you.